arrived in America for a sort of sabbatical. What were you doing there?
I was working as visiting expert at the National Bureau of Standards, working in the Surface Science Laboratory, in particular working with two equally young, raring-to-go scientists, John Yates and Ted Mady. And at that time in the National Bureau of Standards, as often happens purely by chance, there was just this, it became a meeting place of 4 or 5 of us who were the young Turks in the field, each one of us feeling that we were opening the field up in a totally new direction. So taking a study which had been always macroscopic, we knew what the temperature was, what the product reaction rate was, we knew what the catalyst was in terms of its solid properties. We had no atomic or electronic understanding of what was happening. So what we were developing was a new methodology, which was quite challenging because surfaces form a very tiny proportion of a given piece of matter. And we were not going to work with very high surface area materials where the proportion of the matter that is surface is much greater, but with pieces of material that look rather like a one-penny coin. And so we had a very tiny number of atoms that we were trying to work on. So defining these atoms with atomic resolution was going to be our challenge. So we had to take techniques. If you look at crystallography, it had been developed through the development of X-ray techniques. Now, X-rays go right through the solid, and that is their great beauty, and they give you the average structure of the solid. But they're, by that definition, absolutely no use for the surface, because the surface is just a transparent part of the process. So we had to use techniques based around electrons that would be reflected back by the solid, and start working with a whole series of techniques using photons, electrons, helium ions, all sorts of new techniques, and then taking old techniques, infrared spectroscopy was one of them, and developing these old techniques in new ways so that we could apply them. And we became, I think, a rather obstreperous group of young people. So we formed what was called, in a very American way, a Surface Science for Lunch bunch. And we would go through the paper of somebody who was still living in their macroscopic world and pull it to bits. And then we would invite them over to give us a talk and then tear them apart. And we seemed to get a lot of pleasure out of this process. So it was unpleasant in a way, but what it taught me was the business of challenge, which I know I'd always had all my life, was central to good science. That whatever you did in the challenge process, even if at the end of the day you totally agreed with the person you were challenging, the whole thing was made more robust through that challenge process. So we all had the same rather aggressive approach to challenge, and it worked very well. So I mean, I can now look back on that as a massive springboard in the development of surface science. It's not as if we were the only ones doing it. There were other groups emerging at the same time in different parts of the world. But certainly I think that I could say that there were 3 or 4 people who really were responsible for developing modern surface science, and that springboard was a big part of that.
And you're an odd paradox, because you speak very gently and you seem a very gentle sort of person, and yet you're representing yourself as, quite pugnacious and almost aggressive and questioning. And it probably is that combination which made you such a successful Chief Scientific Officer, because when you're dealing with someone like Tony Blair and others, if you're just a bullying type, it won't work at all. If you can be rolled over, it won't work at all. And it's this combination of steely resolve and obstreperousness, as you put it, with, a mildish manner, which you need. Do you think that's fair?
I think it probably is fair, but I think what you've got to feed into that is, I'm particularly in the period when I was in America. I'm talking about a period when I was quite an aggressive young man, so I've matured into what you see in front of you now.
Oh, right. Okay, well, let's come back to this country then again. Is that when you went to Liverpool?
So I was at Imperial College for 3 years. Again, very exciting years. Then went to the University of East Anglia.
Oh, that's right.
My first teaching post was as a lecturer at the University of East Anglia in chemical physics, where I was thrown into the deep end. You'll do first year thermodynamics. Imagine this new university, new bunch of people. You'll do thermodynamics, you'll do spectroscopy, and at the end of the first year, the head of physical chemistry, a lovely man, Norman Shepherd, called me into his office and said, the lowest marks in the examination in chemistry were for your course on thermodynamics. You managed to pass 2 students, and the rest are all fails. I think you need to re-examine how you teach thermodynamics. And this was a big awakening for me, and again, critically important, was the realization that I had to understand as if I was the student rather than as if I was just broadcasting. And I spent 2 months preparing my thermodynamics course. I re-evaluated the whole business of teaching thermodynamics, which is a very mathematical and abstract part of a physics or chemistry course, but it can be made much less abstract by dwelling on concepts. And so I began to develop a new mode of teaching thermodynamics, which was to capture interest around concepts and then develop the mathematics behind it. This sometimes horrified my colleagues. So one of my essays that I set for the students, and setting essays wasn't common in thermodynamics, was to give them a cartoon I'd found from the New Yorker of a man running up a steep slope, followed by a boulder that was rolling up the slope after him. And my essay simply said, discuss. So, the notion of energy conservation, second law of thermodynamics and entropy, all of that was bound into this cartoon. And for these young people, this was fascinating. Entropy was often seen to be the ultimate in the abstract concept. And I had to start by explaining to them that I thought energy was a much more difficult idea than entropy. And that was a way in which I could capture their interest. Now, the reason I'm emphasizing this before you get me to Liverpool is that this was a very important step in terms of my eventually becoming a chief scientific advisor. This was the ability to explain and capture the interest of people. And I do think that I hadn't even got close to that when I arrived at the University of East Anglia. 8 years later, I think I had honed that into something that was really worthwhile.
And you enjoyed teaching?
I thoroughly enjoyed teaching. All my life, the privilege of being a teacher, researcher in the university, interacting with these bright young people has just been what has made my life so pleasant.
Which part of it do you like most or least? I mean, did you go through the supervision? I mean, when you came to Cambridge, certainly 1-to-1, 1-to-2 kind of supervision.
Yeah, I came to Cambridge quite late, and so by the time I came to Cambridge, I was head of physical chemistry and didn't do much supervision at all. I only did supervision because I wanted to do it. I was at St John's College, and not because I was required to supervise at all. So both at the University of East Anglia and the University of Liverpool, my teaching was all in smaller groups, but maybe 10, 12 students at a time. But I really enjoyed all of those times. Interestingly, not so much in the practical laboratories. That was a bit of a chore. whereas the discussions and this notion of saying, well, these concepts don't only apply to what you've got on the bench there. These concepts apply to the real world that we live in, and we can bring a lot of them back to the bench. So the teaching of thermodynamics, spectroscopy, quantum mechanics, statistical mechanics, all of these things was a big learning process for me. You know, what I thought I understood when I was an undergraduate, I realized as I moved on, had been a very superficial grasp of how it all worked. And by the time I got into government, I think I had developed this into an overall view of science. And I realized although I was trained as a chemical physicist, I could use these concepts applied to virtually any aspect of science.
And were you interested in the history and philosophy of science as a subject?
I was interested in the philosophy of science, and this then drew me into the history rather than the other way around. And I mean the philosophy of science, however, also led me to the limitations of science. This doesn't take me into religion; it rather takes me into the world of existentialism, closer to Buddhist than any other form of religion.
That's interesting. Let's just return to your actual central work as a research scientist before we get on to politics and government. You may not want to comment on this, but certainly in the Wikipedia article on it, there's a dark allusion to the fact that there were three of you, and I've forgotten the other two names, who were working on a very, very important theory, and in the end, one of you, the three of you, got a Nobel Prize, and you didn't. We were referred to an article about this, which I hadn't seen. Can you explain? That was obviously one of the more important pieces of work you've done.
You obviously ought to read Wikipedia, but certainly I was honoured by the University College London with an honorary degree, and the orator did say there were three people who have been attributed with developing modern surface science, King, Ertl and Sanajai, of whom only Ertl got the Nobel Prize. So that would match up with what you're saying.
Yes. What was that? Is that what the work that you were describing earlier? Really?
Yes. No, that is my lifetime's work. So even beginning back in South Africa with my PhD and not being happy with that rather macroscopic and rough view of the world. The analogy, by the way, is easy to make with biology and molecular biology.
Yes.
So this was taking catalysis from that rough description into an atomic view of what was happening. And I used that as a model for developing modern surface science. So the three of us, Gabor, Sanajai, Gerhard Ertl and myself are close friends, and nothing would change that. And we have interacted with each other over a period of many decades. The field has undergone a massive transformation to the point where in the laboratory here in Cambridge today, I've just been looking at the latest study of the structure of water molecules on a metal surface, where we have managed to pinpoint where all the oxygen atoms and hydrogen atoms are in quite a complex structure. And why am I excited about this? Because water molecules have evaded our ability to work on them until just the last couple of years, the culmination being this wonderful revelation this morning. Water molecules is very difficult because we had to use electrons so that we got surface sensitivity. But electrons were breaking the molecules down before we could determine their structure. So So we had to develop a piece of equipment that was about 1 million times more sensitive than previous equipment. And this is our first result emerging from that. That little description there is just one step of what we've been doing all this time. It's continually refining techniques and then managing to work at the limits of sensitivity. It's not, I mean, part of it has been the excitement of imaging atoms, imaging and manipulating individual atoms. So that in itself, people writing words with atoms, which is a bit of fun. But that in itself just signifies this amazing transformation. We have these, we are unique here in Cambridge in pulling together development of new instruments and development of new theories. So we bring both state-of-the-art together, quantum theory and development of new instruments, each pushing the other. So the state of the quantum theory is so good that sometimes I'm not sure which is more accurate, the experiment or the theory. And therefore, the whole object of the game is to try and develop ways of using surfaces in the computer and then taking that knowledge back into the laboratory and making something work. So for example, car exhaust system is a dreadful poisonous piece of apparatus. The combustion engine is awful. So emitting carbon monoxide, suicides would just attach a hose pipe and put in the car to kill themselves. And we were filling the air with it. The cities like Los Angeles and San Francisco disappearing under a haze of automobile exhaust, basically. Now, what is in the back end of the modern car exhaust is a catalytic system which converts these noxious gases into harmless gases. That's what we've been working on trying to improve, but using fundamental knowledge rather than just random trial. Yes, so there is that story about the Nobel Prize, which is very recent and therefore quite raw.
Okay, well, we'll probably leave it at that. I was struck when you were talking that of memories of interviewing Lord Rees, Martin Rees, because he very forcefully said that the improvements in measurement techniques and technology of observation as an astronomer had been what had really driven the advances in astronomy in the last 20, 30, 40 years. It sounds as if that's the case with you as well.
Absolutely astonishing. The idea 40 years ago that we would be able to image every single atom in the surface, actually image each atom, would have been a total dream. In other words, you would have been declared mad if you thought you could ever achieve that. Just to get some average property of these surface atoms was already a dream. But to pick them out individually and then actually not just pick them out, but measure their properties one at a time. So yes, this is the equivalent of better instrumentation in astronomy.
One sort of last question in this sort of area. I often ask distinguished scientists if they were giving advice to a young scientist about how to do as well as they possibly could. I mean, some of them say don't go into science, but others have some fruits of their years. And I was wondering if you advised to a young scientist, what one or two points would you make to them?
If I was to give advice to a young scientist, I would certainly categorize my advice in two different ways. One is, how do you optimize your own ability to develop your talents? And so that would be a very general piece of advice, and I suspect would apply to almost any area of study. You need to follow your own interests, and at the same time, attach yourself to a master, become an apprentice to an expert. That is, I think, critically important, because you can be utterly brilliant and well find the right texts to read and so on, and through that develop into a brilliant scientist. But the shortcut is to develop your trade through an apprenticeship. So my attitude towards a PhD studentship is that it is a period of apprenticeship. I never would abandon a PhD student in the corner of a lab to sort out the PhD all by themselves. I think it's critically important to surround them with an intellectual environment which is continually challenging and developing their ability. But the second part of my advice would be, what would be the best areas to get into today? And I'm fairly clear about this in the sense that you could choose to go into particle physics if you're a brilliant mathematical-minded physicist. Go to CERN, hope that after CERN there's going to be the next stage of CERN, an even bigger accelerator, eventually perhaps one going right round the planet. And I suspect you might discover that humanity is getting less and less interested in going further and further back in time. In other words, we've now got to sub-microsecond after the Big Bang. There's no stopping that. You can go back to a millionth of a second, from a millionth to a billionth of a second to a trillionth of a second. There's no stopping that, and you can keep working at higher energies. I think we know enough about that, frankly, and especially given the enormous cost in terms of talented people and the cost of building the equipment. So I would rather say, look at what is challenging humanity today. We have a completely new set of challenges, all arising from the fact that by mid-century we'll be 9 billion people on this planet. We will have run out of a whole bunch of resources that we're all taking for granted at the moment, and at the same time those 9 billion people will therefore have to manage with a more restricted set of resources. And then there's another bunch of resources we're totally mismanaging, in particular the atmosphere and the ocean, but also land. We can recover land a little more easily. There I'm setting out a set of challenges, whether you're interested in the life sciences, the physical sciences, engineering. I'm suggesting that your talents can be best made use of by moving into one of these very demanding areas. How do we, if you're an economist, how do we move into a new design of economics or attitude towards economics in which we look at sustainability as the most important thing, rather than GDP growth, which is what we've had for many years. If we're looking at physics and engineering, what do we use as alternatives to energy sources from fossil fuels? Yes, we've got nuclear energy, we've got solar energy, we've got wind, we've got geothermal energy. How do we mine those forms of energy efficiently for all of our uses? If we look at the question of mobility, how do we get around? Now, each of these problems may sound very practical, but each one of these has a fundamental edge to it, so you can tackle these at any level. Those are my two approaches to advice.
Well, that's very interesting. Leads on perhaps to a question I usually ask is, how do you work? That is to say, some people go for long walks and suddenly ideas pop into their heads, others sit in the bath or listen to music or sit and work in labs. I mean, not necessarily eureka moments, but what is most conducive to your personal thinking?
I think obsessiveness. So I suspect the common trait of the scientist is obsessiveness. So we scientists may even have a tendency towards Asperger's, but we can really on problems. And I certainly am not dog with a bone. Give me a problem and I haven't solved it. And it's in my mind constantly. So I may appear to be having a meal with a group of friends, but actually in the back of my mind this is still there. So I do think that sort of obsessiveness is absolutely vital. I don't actually know what happens when I'm obsessed with a problem. It's not as if I am feeling as if I'm totally focused on it. I'm aware of it, and I know because there's a kind of sense of tension and frustration. But what does emerge is best described as a eureka moment, because there's a point of clarity with which it all seems to fall into place. And when I was younger, that used to come as a complete surprise. Now it doesn't happen quite so instantaneously. I can see it all emerging and all slowly now. But my greatest eureka moment was sitting with some stunning results. So that means unexpected, so requiring a new explanation. And PhD student Alison Crossley, who's based in Oxfordshire, and we're still in contact with each other. 1975 this was, Liverpool. And we had been sitting until 10 one evening, all day, trying to sort this out. Couldn't sort it out. And 4 o'clock in the morning I woke up and there it was. And I had to get up and write it down. And then I just couldn't sit there because I wanted to go and tell him. But the decent thing was to wait until a decent hour. So I waited until 7 a.m. jumped in my car and drove into town. I'm afraid at quite a speed, so I was stopped by a policeman and received a speeding fine. I was so elated, I didn't mind one little bit.
What a lovely story. Rather like that famous mathematician Ramanujan, or whose solutions came usually at about 4 in the morning from some Hindu goddess or something.
Right.
And of course, you know Newton's remark when he was asked how he had done what he did. He said, by thinking on it all the time.
Right.
Or thinking on it all the time.
But for most of us, I suspect it's not that you're consciously trying to think on it all the time, but that you can't let it go.
As with Poincaré's descriptions of scientific, he's not thinking about the problem formally, but then suddenly he realizes he has been thinking about it. Let's now, that was fascinating. Let's now go to your involvement with government. Where should we start? When you became Chief Scientific Officer, or
Title is Chief Scientific Advisor.
Advisor, yeah.
And it was in October 2000. All very short notice. Offered the job in July 2000. Please, could you start in October? I was Master of Downing, Head of Chemistry at Cambridge, and it didn't seem possible, and I wasn't even sure it was desirable. Looking at a job in government was a total black box to me. I had been completely engrossed by my work in Cambridge. So being Master of College, Head of a department, and I had a research group of 25 people, was taking up all my time, and I had avoided taking any jobs in government or research councils or whatever. So I had no preparation for this apart from my government experience against government, if you like, in South Africa. When I came out into this country, for a period I worked for the Association of University Teachers, and when I was professor at Liverpool I became president of the Association of University Teachers. So I had that sort of political inclination, and that was what created the interest. I was headhunted for the post. Accepted, and part start of 1st of October, relinquished all my work except the research, including chairmanship of Kettle's Yard, from January the 1st, 2001. So it was really full-time from January the 1st, 2001. My major objective was to try to get governments moving on the issue of climate change, which I told all my friends, including Gabriel Horn. What I immediately did was set about a study of the state of energy research in the United Kingdom. So there was this fascinating discovery that here we were about to go into a period when we needed to find alternative forms of energy other than fossil fuel based, and yet our report showed that energy research had totally collapsed. We had the biggest energy research laboratory in Europe, which was the Central Electricity Generating Board Research Laboratory, and the Gas Board also had a research laboratory that was big and well known. When electricity and gas were privatised, the casualty that had hardly been picked up was that all of the utilities that were formed immediately shut down the research laboratories they inherited. We all know they sweated their assets in economic terms. So the capability for research in Britain had more or less come grinding to a halt. That was the outcome of this piece of work. But just when we were getting this underway, we had the foot and mouth disease epidemic, which began in, well, we now know it began on February the 23rd is the closest date we can put it to, in 2001. I got involved in about March the 7th, March the 10th, reading the newspapers actually, and thinking, was this what the Chief Scientific Advisor's job was about? It was all being handled within what was then the Ministry of Agriculture, Food and Fisheries, and they had their own scientist, they had a Chief Veterinary Officer, and I thought I should leave them to operate on their own. But as I watched this epidemic take off around the country and saw that it was just growing exponentially, I thought maybe I ought to take an active interest. And John Krebs, now Lord Krebs, and I got together a team of people who are partly government people and partly external to government, professors. And we just discussed what was happening and decided what we needed to do was to model the thing. Just as an interesting aside, my interest in solid surfaces, molecules on solid surfaces, had taken me to one piece of work we'd done on the way molecules move around surfaces. And this rather elaborate model that we had published in the 1980s, I now realized was rather like a virus moving around farms. Farms are two-dimensional, like surfaces. Quaintly, on average, a British farm has got 5 nearest neighbours, by which I mean it has a contiguous boundary with the first neighbour. And we were able to set up models, both all farm, all animal models in the computer. This was done by a Cambridge group, not my own, and a simple model that was based on the sort of algebra I'd been developing, which was based on how many near neighbours there were to a given site on a surface or a farmland on land. The two models gave much the same results, so we were able to have a theoretical description of this epidemic in its early stages. We then therefore knew what the rate of infectivity was going from an infected farm to the neighbouring farms and to the next neighbour circle of farms and so on. And from that analysis we very quickly realised that this epidemic was completely different from the 1967-68 epidemic in Britain. That epidemic had been very heavily driven by wind-borne disease, and essentially the reason it turns out is because it was driven by pigs, and pigs yield actually from both ends of the animal a very large cloud of aerosol that carries the virus, that gets up into the wind, and the wind. So the direction of the wind was critical to deciding where the next farms were that were vulnerable. In the 2001 epidemic, however, it must have been animals virtually touching across fences that was causing it, because the epidemic was spreading locally from one farm to the next. So I realized that what MAF had done, the ministry had done, was simply take out the lessons learned from the 67-68 epidemic and applied them, and they were not actually relevant. The other thing we learned was that the epidemic, instead of just growing as it was and developed by wind directions, would suddenly pop up all over the country. And that turned out to be non-random. In essence, it meant animals were sent to, animals were born on a farm somewhere. They were then sent off to be fattened somewhere else, as young animals, sent off somewhere else because the season had changed and they'd be better off at the bottom of the hills rather than the top. And they were sent to large distances around the country. This hadn't happened in 67, 68. So farming has become a very much more honed practice in which the farmers are optimizing the development of their animals and preparing them for market. And so much more animal movement. Total surprise to MAF, who were using models based on 67, 68. So all of our modelling revealed these surprises, and we began to understand what was happening. And we now had a computer program in which we could try different strategies for bringing this thing to an end. And within that computer program, the PC model could be just run very quickly. We were using the big Cambridge model as a way of just checking that we were getting results that on the simple PC model that were good. So March 22nd, I went in to see the Prime Minister, and this was my first meeting with the Prime Minister. Say, you've got
this was Tony Blair.
Yes, you've got this epidemic running. This is what's happening. But Prime Minister, we've done the analysis, and we can switch it off in 2 days. We can turn exponential rise to exponential decay within 2 days, if you follow the procedure we've used in our models. And the procedure was, as soon as a farm goes down with a disease, you send in a vet. If the vet confirms what the farmer thinks, then you immediately take the animals out. Don't take a blood sample. Take a blood sample, but don't wait until it's been analysed. You take those animals out immediately. But as soon as the sample's been analysed, and that would take typically 6 days, as soon as it's been analysed and you find it's positive, confirms what the vet thinks, you now immediately take all of the near-neighbour farms out. Because by that time, a good number of those animals are already developing the virus. But if we do that, we can virtually stop the spread of this disease, because this is the way it behaves in a computer. Well, the Prime Minister was quite pleased.
Imagine.
So he called together a meeting of COBRA down in the basement, and so all departments represented, and I said, right, tell them what's going to be done. And he said, I'm putting you in charge now. Let's see, you have a science meeting every day, report to me morning and evening, and off we went. We did actually have the sense, fortunately, to have an army expert do logistical modelling for us. And I was able to say, Prime Minister, today you've got 45 new infected farms reported across England and Wales. And in 9 days' time, if you carry on the way we're going at the moment, you will have 90. I'm giving you a route forward which will turn this around within 2 days. By the time that's happened, we will have peaked at about 50 new farms, and then we'll drop. If we get beyond 60, the Army tell us that they have not got the capacity to carry through the operation we're planning. So we need to operate right away. and that was it. That was it. I was immediately, that next day, I was sent out onto television and radio by the Prime Minister to explain why policy had changed. What I didn't realise the first time I went on radio was that the Minister for Agriculture, Food and Fisheries...
John Gummer, was it?
No, it wasn't. This was Tony Blair's minister.
Oh, yes.
Brown.
Oh, yes.
Not Gordon Brown.
Mm.
Why have I forgotten his first name? Perhaps I'm blocking it. So he had gone out on a big press conference, radio, television cameras flowing, saying, it's all right, everything's under control. And my very first television appearance, I went out saying, this is out of control at the moment, but we need to follow the following procedures to get it under control, and we will get it under control within 2 days. And the person interviewing me said, but we've just had the minister saying it's perfectly under control. So I had to explain that out of control was a scientific statement, that the R0 term for the epidemic was actually greater than 1. That is, for each new infected farm going down today, tomorrow there'd be more than 1 new infected farm. And the disease under control, tomorrow there'd be less than 1. And so I had to use science to explain the difference. And the minister was saying it's all under control because our process would bring it under control.
Well done.
The upshot, however, was we brought it under control. I showed my curves on television, predicting how this would go. Richard Wilson called me in, head of the civil service, and said, David, do you know what's happening? I said, well, I think I've got it all under control. And he said, no, I mean, you are in a very dangerous personal position because you're being sent out to explain what's being done. There's no politician out there next to you. If this doesn't work, then they can all point to you and say it was his advice that didn't work. I said, Richard, I'm pretty confident. We've gone through all this. Anyway, the data points came in, and I'm very pleased to say the data points followed that curve amazingly well, far too well. The date of the general election was due on May the 5th. Everyone knew that year, and it was delayed until, I think it was June the 7th or 8th. And I know that date was chosen on the basis of my curves, because May the 5th the epidemic would have been very high, but by June the 7th we have it fully under control. So I think it is the first time the date of the general election has been chosen on the basis of scientific calculation.
What a lovely story. And this obviously must have pleased your master, Tony Blair, and had you already started, well, you hadn't met him, but had you tried to put climate change at the front of scientific endeavour at that point, or was it later after this, harvesting the goodwill of this, that you managed to persuade him?
As a matter of fact, my first trip to Washington was just after President Bush had declared that Kyoto was dead, which I believe was early February 2001. So actually I went to Washington as the foot and mouth disease epidemic began, but unwittingly. I think the amusing bit about the trip was it was both to deal with Bush's anger over Europe declaring that they didn't want any American food that contained genetically modified foodstuffs. He claimed that was a trade barrier, and I had to go over and explain that Britain, for a starter, was going to make a lot of money out of genetically modified foodstuffs. We in Cambridge had invented molecular biology and planned to make good use of what we'd invented, and at the same time I needed to explain why it was that Kyoto shouldn't be gay. I went on this mission with a man called Michael Arthur, and so my first mission was called the King Arthur mission. And we went into the White House, and we were very politely received on both issues, and I did meet a whole range of highly positioned people in the cabinet. I didn't meet George Bush at the time, but his personal advisors. We were given a very polite hearing, and on both issues, however, there was a pretty negative response. So I was already beginning to move. The Prime Minister asked me to go to deal with the GM question, and I asked if I could add the climate change issue as well. I think it would be fair to say that Blair's focus from science was on the science, innovation, wealth creation agenda. And so in that first year, 2001, I persuaded him to do a speech. I think it's the first full 1 hour speech any Prime Minister has given to the Royal Society on science. And he gave his speech under the title of Science Matters. And so I was heavily involved in the preparation of that speech and saw Tony Blair in his most astonishing speech-making capability at first hand. So the speech took 3 or 4 months to prepare. There was a team of 3 or 4 of us involved in the preparation, and he was involved in discussions with us roughly once a month in the lead up to the speech. And then in the last 2 nights before the speech, he began rewriting it, despite his own engagement in it. And as he often did, the night before the actual speech, stayed up until the early hours of the morning. Those amazing speeches that he gave, he put an awful lot of effort into. And so he would rewrite and then virtually memorize as he went through that process. Now the science, he did read a fair bit more of the speech out than he normally does. But nevertheless, this was the big statement that Britain was extraordinarily strong in the science space, and we needed to keep building it up at twice the rate of our GDP growth. And so the commitment that the science space would be funded at twice the rate of GDP growth was included then. And the speech talks a lot about how molecular biology was invented here and how we should benefit from the technologies that emerge. I think for me the fascinating thing was that the following year Premier Wen Jiabao from China had a state visit, and he was of course seeing the Queen and the Prime Minister, and from the embassy came a message, and he would like to meet the Government Chief Scientific Advisor. Now, needless to say, in the list, the food chain in Britain, I was very much at the bottom, and so it was a little surprising that he was requesting for me to move. And in the end, I met him on a Sunday. It didn't happen officially. And I did take a group of vice-chancellors along with me. But he did tell me, when I asked why he'd asked to meet me. I mean, first of all, for a Chinese Prime Minister, it's not a surprise to meet a chief scientist. Half of his Politburo are engineers or scientists. Science has a very high status in China. But secondly, it turns out Science Matters had been translated into Chinese, and he said, we have altered Chinese policy to match what was written there, and I wanted to talk to the man who had advised his Prime Minister down this route. So this began a very strong relationship that I maintained with the Chinese, much stronger than with the Bush regime, actually, over the following years. It meant that I brought China into the world's biggest ever technological project, the ITER project, which became my big baby. It meant that I was able to advise them on climate change. We took our team who developed Britain's approach to adapting to the challenges of climate change in flooding coastal defences. We took our team out to China to work in the area around Shanghai, the Yangtze Basin area, and I have personally no doubt that what turned the Politburo's decision making on climate change around 2.5 years ago was receiving a report from their own scientists, engineers and economists on the impact on the Yangtze Basin area. Shanghai, by the end of the century, if the world doesn't manage this problem, goes underwater. Flooding from the Yangtze and flooding from ocean, sea levels rising, would make it unmanageable. That beginning with meeting up with Premier Wen Jiabao on his state visit here has led to quite a fruitful outcome in terms of
only yesterday, I think, the Chinese announced their emissions targets. Yes.
So I've been into Beijing this year, and I had put the idea to a rather astonished climate change advisor to the President and the Premier, that if he and President Obama were able to stand on a platform together and declare what needs to be done with climate change, the rest of the world would follow. Now, it didn't quite happen that way because President Obama couldn't, without his Senate approval, reach that point, but it came pretty close.
It's getting closer, I think, is something. I mean, this is slightly off the point, but I did an interview with Richard Friend, and he talked about his work with plastics and energy capture from solar energy using a much cheaper form of capturing material, which you will know about. I mean, that seems a very promising direction. You know that you know about this.
I more than know about it, in the sense that I got Richard Friend to make a presentation to the Prime Minister on this, and I have been pressing to create. You see, I think this is so important that it's worth the British government investing taxpayers' money in setting up a sufficient investment into the base around Cambridge to enable these spin-out companies that are developing these ideas to really compete at the world level. I think what we've always missed in the past is backing really good ideas by British government funding. Now, we've got several hundred million going into this now, and my hope is that it's not only plastic photovoltaics, which will be far cheaper than silicon-based photovoltaics, but it's also plastic-based computer hardware. They can actually eliminate silicon from future computers.
I mean, he showed me his reader as well, the one that's coming out in January.
Right.
You know, this extraordinary flat roll-up thing. And I also interviewed Herman Hauser, who has backed him, and he showed me the device. I mean, it seems such an exciting area.
I honestly think this, if we get this right, this will ensure the financial future of the United Kingdom. I mean, we won't need to survive with bankers doing what they do.
And also save the planet, hopefully, on the way.
And also save the planet. I mean, I think the idea of being able to cover every building with material that turns solar energy into electricity, this is a bit unfortunate.
So I didn't record that. If we could coat all these buildings, and also, as Richard Friend said, you know, a small state like Kansas covered with this stuff would provide all the power for America. If you had, and the Chinese are quite interested in this, I think, you had sort of 4 or 5 of these areas covered, plus all the buildings and cars and everything. I mean, you have free, non-polluting energy. There's the problem of storing it and distributing it, of course, but...
So, the Chinese, I've been introduced to the man who is in charge of energy for China. This is the way China operates. So So I had been sat in front of members of the Politburo and a range of civil servants for a few hours and asked to advise them how to manage climate change. This is a few years ago. And obviously when I was in government and could say nothing about it. And I had essentially told them to do what we introduced in Britain in 2004 and what was rolled out into Europe, which is cap and trade. You put a cap on every nation and you trade carbon dioxide between nations. I said, do it across China and it's your way of taking control of energy. You've got very inefficient energy usage processes in place, and this will drive through alternative energy sources from fossil fuels. And I came back in February this year and met him, and he said, we think you didn't quite understand that we are not a capitalist economy. I said, what do you mean? He said, we have top-down decision making. I've been told what is the maximum amount of coal I can use in any given year, and I have to find alternatives. So he said, that's my job. And if the Politburo tells you to do that, you deliver. So I said, how are you doing it? He said, we are now the world's biggest producer of photovoltaics. So they just switch it on and away they go. They have under construction, nearly completed, a 1 billion watt power station, which is entirely photovoltaic.
Gosh.
They're covering a piece of the desert, and this is using silicon-based photovoltaics. Now, if you took Richard Friend's plastic photovoltaics, you could do that everywhere.
Exactly.
At a tiny fraction of the cost to the Chinese government. I think, and just to finish the Chinese side of the story, they've now, of course, got the world's biggest program of building new nuclear power stations. So they're facing up to the alternatives. Energy efficiency, that was the announcement the day before yesterday from President Hu Jintao. They are totally caught up now in managing the problem of growing their economy and decreasing their dependence on fossil fuels. The idea of using plastics has so many attractions. It's lowering the cost. It's attractive for architects to use on the outside of buildings. Plastics come in all forms and shapes and colours. And it also means that we can hope to develop ceramics, tiles that are photovoltaic. We can hope to develop paint that is photovoltaic. So what we can do is convert quite a high percentage of the sunlight hitting the planet into the energy we need. And the problem is virtually solved.
If we can get Richard said that the problem at the moment was getting the capture ratio up from about 7% to about 15-16%, which
15
is what...
15 to 20 would be absolutely great.
But he seemed to think this was feasible.
Well, if you think of the amount of work that's been done on silicon today by thousands of people, and how little work has been done on the plastic material, you can be pretty sure it's right.
We've only got 3 minutes left. Is there anything you'd really like me to ask you about? I haven't asked you about Tony Blair and the Iraq War. Perhaps we should leave that at the moment. But is there something we haven't talked about damming, your mastership there? But what would be your final choice?
I think I've had the most amazingly privileged existence. Not only working with all these young people and all their attributes and being kept lively and young through that, but living in this place, Cambridge, and then I'm now also living in Oxford, experiencing government from within, making friends with the most surprising people. Gorbachev, who's I see as two of the greatest political characters of the 20th century who really made a transformed world possible, were Nelson Mandela, showing that you could have a transformation without violence, and Gorbachev, who's we're just celebrating 20
Mm.
years of the Berlin Wall coming down.
Mm.
Who would have believed it would ever come
Mm.
down? And you know, the breakup of the Soviet Union, the end of communist state period. Remarkable man, and meeting him and getting to know him, getting to know all of these personalities. That's just been such a privilege. Tam Diel,
Mm.
the senior parliamentarian
Mm.
of the UK, a man who I admired enormously for his courage, his tenacity, his
Mm.
challenging of Margaret Thatcher
Mm.
during the Falklands War. Remember the
Mm.
Belgranos?
Mm. Actually, this is in a way a very nice way to end it,
Right.
David, because it sort of shows
I'm still engaged.
that you're sitting here in a quiet and very thoughtful, meditative state, but you know, all the time people are wanting you to comment on this and do this and do that. So,
I mean, just to finish that sentence, the privilege of meeting Tam Diel, a real sort of iconic figure for me, and then Tam and I became friends. We sort of met up. They invited me for lunch at the House of Commons, and it turns out that we just both enjoyed each other's company. I never imagined I would meet people like that. So it's just been stunning. I enjoyed every moment of being in government. But just as I enjoyed every moment of working in chemistry here and down, it's been tremendous. And my new life in Oxford. I know I'm not supposed to mention that.
no, don't mention Oxford. Thank you very much indeed, David.
Thank you.